Nobel Prize in Physics for his work with the Cosmic Background Explorer, which is a satellite that mapped the cosmic background radiation. That is the energy, the heat, literally, left over from the Big Bang. He is an expert in cosmology, and he's going to tell you all about it. My friends, it's my honor to welcome to the Starmus Earth stage, George Smoot!
I'll have to move only by one C as control. Some control, I'll move only one C, Thank you. It's a pleasure to be here. So thank you, Starmus and Bratislava. And I want you to know I'm wearing the tie I wore to the very first Starmus. And I was sitting on a panel and Neil Armstrong was taking notes to ask me questions later. So it can't be that bad. I'm showing a little movie which is going to be obsolete. This is flying through 2 million galaxies. And these are pictures of the real galaxies in their real place in space. But I haven't got very long to tell you the secrets of the universe. And so we got to move on to showing the slides. So, the title of my talk that Garrick liked and wanted, Cosmology Today and Tomorrow. I'm going to do a little tiny bit of history, and then I'm going to tell you things that are really new. Because that's more interesting for me, but I don't know how fast I can get through it. So, we're going to have to go through it. So, we have a simple idea of the universe. It popped out of nothing. It inflated in an accelerating expansion of space. It slowed down, during that time it slowed down, it made the stars and the galaxies, and then it started expanding more rapidly into what we call an ESET phase, but an exponentially expanding phase. This is already seems a little fanciful, but in fact, we have a lot of good data and observations about this. Modern cosmology started now 120 years ago. I remember it was only 100 years ago. And so it started with Edwin Hubble, and he got to use the biggest telescope there was at the time. There's a picture of him sitting at the fine focus. And he started observing the things that were called nebulae in those days. And there was an argument going on, is there just one big island universe, or are there more island universes out there, which we now call galaxies? And he was looking at the Andromeda Nebula, and he saw 7 variable stars that we're doing, that Henrietta Swan Leavitt, so down here at the bottom of the picture, and credit, she discovered there were 2 kinds of these stars that are called 7 variables, and they oscillate with a brightness that's also linearly proportional to its frequency. So if you measure its frequency, you know its absolute brightness, and you can estimate how far away it is. And he did that, and he found the Andromeda Nebula was 2.3 million light years away. That was well far away from all the other structures that we do, and it meant that it was a separate galaxy, a separate island universe. On the left is the original data that Hubble published and declared the universal law of expansion. I mean, there's a limited amount of data, and this is one of the first universal laws. Newton's law of gravity was the other first universal law. And there's a little tiny square on the figure on the right, which I can point to, but I can't, laser to. There's that same data, and here is the present state of the art, where on the bottom axis is essentially the redshift, or how much the wavelength is stretched, depending on how far away it is, versus the brightness of the object. And you see it's a straight line, and this validates Hubble's wild assertion that the universe was expanding isotropically. And there's a little tiny universe out there expanding, and it's got 2 galaxies on it, and a light wave traveling between it. The 2 galaxies stay the same size, but the light wave gets stretched. So that has to do with the nature of light versus the nature of orbiting particles readjusting their orbits to stay the same. that already gets complicated, but we don't have to worry about it. What you have to do is be amazed at how well that law goes out. And that law goes out now to a redshift of 1, 10 to the 0. So out to a redshift of 1, this is tremendously far out compared to what we're used to. Okay, so we might as well get a little wilder and say, well, it's the beginning of time. There's some quantum fluctuations followed by a region that goes through inflation and makes the whole observable universe you see today, plus probably a lot more, at 380,000 years. My team and then succeeding teams now have observed the fluctuations of that early universe. And here, 13.7 billion years later, we see those galaxies that we're flying through. Okay? Well, that's a pretty simple model, right? Well, let's fill in some details. So here's some plots I made. The plot on the top, on the left, is a plot of the observations of the cosmic microwave background. Penzias and Wilson discovered this in 1964, published in 65. Penzias died about 3 months ago. They got the Nobel Prize for that, and that was Wilson's first scientific paper. So you guys should aim for that. and I made this plot. Those points in red, you see Penzias and Wilson pulled out there. Those points in red were points that my group worked on for several years, from Berkeley and from White Mountain. And then at the top, in the green and the blue, are the data we got from the Kobe satellite, which, because this is a log plot, really covers 90% of the total energy that's in the cosmic microwave background. It showed that it's completely thermal in nature. That is, the early universe was hot and uniform and well described by simply a simple thermodynamic state. The next figure is one I made below, which I can't believe it was nearly 35 years ago, was in 1982 when we announced the discovery of anisotropy in this radiation. That is, we're using this radiation to make an image of the universe back when it was 400,000 years old. Now that doesn't seem, like an early time, but in human, if the universe was middle-aged today, this would be a human about 12 to 20 hours after conception. So this is really the embryo universe. So first you see it's extraordinarily uniform, but if you zoom in a factor of 1,000, you see there's a smooth curve there where it goes from hot in the upper right to blue in the lower left, and it follows a cosine almost exactly, and there's only a couple little dots. One of those, as you see in the blue, that's the spiral arm of the galaxy that we're in, and it looks bright because there's a lot of activity in the spiral arm. And the other side of the red spot is look at the other way down the spiral arm, and in the middle, you can see the middle of our galaxy. But that's a part in 1,000. That means we're moving relative to that radiation at about a part in 1,000 the speed of light. If you take that away and blow the scale up by almost a factor of 1,000 again, you find the galaxy is saturated with red, but on this side you see some blue and yellow and red spots, and blue and yellow red spots on the bottom. Those were structures that were existed in the universe when the universe was 400,000 years old. And they're the things that grow to be some of the interesting things we see today. And so, being bold, we made up a plot like the one on the right that says, okay, there was a Big Bang, there was inflation, we made space, time, we also made fluctuations, and then we got to make, the basic particles, and then we got to make protons and neutrons, and then we got to make atoms, and the universe got to be transparent, we got to see it, and eventually we got to make galaxies and stars, and more complicated and milder structures like human life. And we had to modify this is 2014 version, we had to modify this because we found the universe was accelerating again at the end. And we have data on this, and that's what we're seeing today. There are other tools and instruments. This is a picture of the Hubble spacecraft. And if you look out to what's called the Hubble Deep Field, you're looking back to when the universe was only 1 billion years old. Remember, it's 13.7 now. You can look there and you get these pictures of beautiful galaxies, and they're pretty well developed. And if you go to the Hubble Deep Field, you're looking at a time period which is between 400 million years and 700 million years after the Big Bang. Now with JWST, we're actually trying to look a little closer, and I have students and a postdoc and colleagues. We're trying to use clusters of galaxies as gravitational lenses to magnify the very early galaxies so we can get more data and understand them better. And so that stuff continues going on. We're still studying, we're still understanding things. Okay. So now here's some of the data. And I'm going to show you two pictures that were made back more than 10 years ago. But when the data from the cosmic microwave background was telling the universe was pretty close to flat, but not necessarily exactly, the supernova was telling us that we have an accelerating universe. There's a thing called variant oscillations, and they come together at a place in which roughly 2/3 of the energy is dark energy, and 1/3 of the energy is in matter, and that the universe is close to flat. About that same time, people you did, I will tell you more about me, the clusters gave basically the same kind of data, and the combined data keep pointing to a flat universe with minimal fluctuations, 10 to minus 5 or slightly lower levels, and the formation of these structures, but the requirement for the dark energy also. So generally, it's between 60% and 70% dark energy, and about 30% matter, 25% dark matter, and the 4.5%, the ordinary matter we're used to. But of that, only 0.03% is the stuff that's in this room, or the whole Earth, in fact. That's the heavier elements. That's very rare stuff. Okay, so I'm going to show you only a couple of equations, but this is the one. So Alexander Friedman, who was a very good Russian meteorologist who really knew how to solve equations, well, it turned out doing Einstein equation was pretty straightforward, and he just made a simple assumption that the universe is the same in all directions, that it's isotropic and homogeneous, and therefore you can reduce four-dimensional equations into two simple equations: an energy conservation equation, the scale factor of the universe, and the acceleration of the universe. And the acceleration of the universe is equal to minus, it's slowing down, gravitational constant, the density plus 3 times the pressure. And so it became easy. Everything in the early universe could basically be treated as a fluid. So in fact, you just need an equation of state, which is the pressure is proportional to the density. And W has got simple versions for cosmological constant. It's -1, means the pressure is a tension, and it means the universe accelerates instead of decelerating. But if you put in ordinary matter, like dark matter, it's 0, it's pressureless, and so on, and photons are third. You could put these in and you could just solve these equations. What he found was there is just no stable universe. The universe has to be expanding or contracting. And Einstein didn't like that. He put the cosmological constant in, but that doesn't save the problem. Okay, so here's the head about what we're going to look at. The top figure is the Kobe measurement. It was followed by the WMAP measurement. And you can see the same features are there, just much more detailed. And then the third one is from the Planck satellite. And there's another satellite in the works, but it's for a different aspect. And there are two ranges of things you see. If you look on the very large scale, you basically see the curvature variations in the universe are almost independent of scale. And there's a slight relativistic effect from expansion of the universe pumping up to very large scales. But then you have a thing we call acoustic peaks and the damping tail. And those acoustic peaks and the damping tail are the ones that tell us about what the universe is made out of in terms of what fluids and how fast it's going. And we try and understand that, and we do the simulations. And I will tell you a little bit more about that in a little bit. But here's what you do if you just say, look at the variance. How much the mean square changes on each angular scale, from a large angular scale, 90 degrees, out to a 20th of a degree, and you see the flat part with a slight rise because of the optical effects, and then you see the peaks, and you see all the oscillations, and it goes out. So that top curve is the temperature variations. The bottom curve is V polarization fluctuations. And you see that, and underneath it, you can see a line, which is our theory. So this is, you know, we're getting tied down, and we're seeing some progress here. And you can then take this two-dimensional map, assume isotropy, collapse it to a one-dimensional map, and do the fit and find the 6 to 7 parameters of the universe that you need in order to describe it with precision that's better than your closed fit. Right? If you go to a tailor, you still have some things, so when you eat meals and do something. Here, we're actually fitting the universe really precisely. Okay, so now here's the thing I'm going to try and teach you. So we start at the left side. There's sort of a Gaussian fluctuation. And this Gaussian fluctuation, you start at time equals 0, and it starts expanding out. A part of the matter decides to go out, and it goes out not just in a circle, it goes out in a sphere around the original perturbation. How does it know which should go out? Because it just does that. Well, the answer is, given on the plot on the right, there's 5 kinds of thing in the universe. There's the dark matter, there's the gas, which is the baryons, that is the hydrogen and helium nuclei plus the electrons that go with them, and photons and neutrinos. So if you watch, you will see we start with the Gaussian and all of them roughly equal, so as it resets, and it separates out, and the baryons and the photons go out coupled until right there they separate. The cosmic microwave background sees when they separate, and then the light comes to you. The people who are going to do the galaxy surveys that I'm going to show you now, they look and see this little spherical shell that appears at the end that is at 150 megaparsecs, which is roughly 400 million light years. And one oscillation is going on. The person who made the simulation there made one too many overlapping, but there are many happening at different places in the universe. And if you look out on the bottom right, you see what the sky should look like. There should be these clusters in the middle with spheres around them. And if you have a good enough telescope, you can count the galaxies and measure the diameter of that sphere in 2 directions by angles. And the third direction, you have to measure the distance with a ruler along that direction, which has to do with using redshifts and interpreting the data carefully. But that's what's going on, but that's what I'm going to show you about one of the new results that just came out. So the observations up to this point have shown a very good fit to the cosmological model, using the one we call lambda CDM. You know, that is, it fits just as well to a cosmological constant in dark matter as it does to other things. But what you can see now, astronomers like to do it in density instead of curvature. Physicists do curvature. The density then goes up as k instead of being flat, and then it peaks up at about 200 million light years, and it rolls off, but you'll notice there are little wiggles. Those are the baryon acoustic oscillations that I was telling you about. Those are the fact that the photon pressure was so hot in the early universe, it just pushed all the atoms away. If we had a galaxy then, it would have blown a galaxy to smithereens. But there was dark matter there, and the dark matter made something for the ordinary matter to fall back on. But if you watch the plot on the left, the extra baryons pull a little bit of dark matter in. So this outer shell has got almost as much dark matter as the core. And we had this little digital sky survey, which the galaxies were issued before, and it measured it and it looked for that. But now I'm going to talk to you about the new results from the dark energy spectrometer instrument, DAISY for short. So Sloan Digital Sky Survey was 2 cubic gigaparsecs. DAISY is 50 gigaparsecs. Now gigaparsec is 3.26 billion light years, so you got to multiply by 3.26 cubed. Right. So you're going to see different phenomena when you look here. When you're looking at it close, you can basically detect any galaxy with your big telescope, because we've got a big telescope now. And when you look further out, you can see the large red galaxies because they're bright enough to see. You can't see the small dwarf galaxies and so forth. And then eventually it's the extremely luminous galaxies. But further out, you see quasi-stellar objects. They're really bright. They're probably black holes in galaxies that are forming and generating a huge amount of almost point light. and all the gases in front of them, you can see absorption lines. So you get from every QSO you have using that. Now the plan was to stay on Bohr's law. On the bottom axis is time, the top axis is the number of galaxies surveyed, and you can see for each survey, the CFA1, which on the stick man, only had nearly 2,000 galaxies. Here, DAISY is looking for 30 million galaxies, and you'll see the next slide, it's actually going to be 40 million now. The Slow Digital Sky Survey had two different versions, but it went out to 2.8 million. So that galaxy survey I was showing you, the ride through, that has 2.8 million, but actually Miguel Allende, the Mexican student who I encouraged, he did it a little earlier, so it's only 2.5 million or 2 million involved in it. But we now have the first results from DAISY. So here is the first results from DAISY. And if you look up on the left, you see this sort of band across the high part. That's the Lyman alpha forest. That's the absorption lines from the QSOs, of which there are 400,000 QSOs spectrum measured. And then in closer is the ones where you can see the individual galaxy and get their lights. And you'll see there's a couple stripes in there. Those are not real stripes of missing areas of galaxy. That's where there was bad weather and that data wasn't taken. It's going to have to be taken in succeeding years. Now, this new data was made available in principle on April 7th. It took a little longer to get out. Here's the basic idea. You've got a big telescope on top of the Kidd Peak and the Mail telescope. It's fitted out with 5,000 optical fibers and 5,000 robot positioners, and they move each little fiber onto a galaxy, and then the light goes down to a spectrograph, and you measure the spectrum very carefully. And so far, it's measured 5.7 billion galaxies, and it's measured 420,000 places. So we're making progress, right? And that's the first year of data. 3 years of data now in the can. A week after that happened, the tray that was holding the 5,000 fibers broke off the telescope. Fortunately, it didn't destroy anything, but it has to be redesigned and re-welded up and put up, so let's see what's going on. And this is what it looks like. This is just a slice. This may be 2 million galaxies in here, but it's just a dot for each galaxy. We haven't got sophisticated and put the postage stamps in the spectrum yet. But you can see these are galaxies. This is not like a planet or whatever. This is individual galaxies, and there are millions of them out there. Okay, so what's the exciting new kind of thing? So if you remember back when I was telling you about Alexander Friedman, he had an equation that said whether the universe is accelerating or decelerating, and it depended on the equation of state. And so one of the first things that DAISY has tried to do using the Baryon acoustic oscillation data is to try and determine what the equation of state is. And so they use a formulation that I suggested 20-something years ago, that W depends on the scale size of the universe. So it wouldn't be depending so strong on redshift. Whatever the present value is, times A1 minus A times the A dependence of it. And if it's cosmological constant, it should be right there where that lambda is, right? And you can see the cross where the lambda is, where, W0 is equal to -1, and WA equals 0, but that's not what the data are saying. But this is a combination of the DAISY experiment, the CMB experiment, and 3 different supernova groups. There are 3 different major groups doing supernova: Pantheon, Union 3, and the DAISY supernova 5-year survey. And as you can see, they say it's away from the cosmological constant, either by 2.5 sigma up to 3.9 sigma. I think this is early. I'm a little scared because it's clearly being driven the most by the supernova. The supernova is pushing things down to this funny area. And we already have an issue with supernova. So this is the Hubble expansion rate at the present time, called the Hubble constant. Although the Hubble expansion rate at the present time is here. In the past, the universe was spinning slower, but it's speeded up, and then it was spinning much faster in the future. And so you actually fit over this whole curve. And if you take just the DAISY, BAO and Big Bang nuclear synthesis, you get this one thick data point in the middle. And if you include the angular size of the C and B, you get a slightly smaller error. And then below that is the tip of the red giant branch. That is a point where stars are getting old and coming to the end of their life. They reach a maximum brightness and they go back down. And that's a way you can tell the distance. And then there is the shoes. And of course, two Starmuses ago, I had an argument with Adam Reeves about this, and it still stayed there, and he's still pushing this, but we'll see what's going to happen. But in both cases, it's the supernova data that are causing there to be some kind of a disjoint, even though those overlap, because the supernova data go out to redshift of 1, and now the variant acoustic oscillations go down to redshift of half. So there's an overlap in the coverage that they have. We have been getting an ever sharpening view of our embryo universe, but also our understanding of what's going on in the universe. So we had Kobe, WMAP, and Planck. We have a bunch of ground-based experiments that we're doing, and they're in the level 3 kind of category. There's the level 4 category. It's been put off a little while. But also, JAXA is going to launch LIGHTBIRD, which is looking to try and see the variations from inflation. So you heard about quantum fluctuations in vacuum. It turns out most of the stuff we're seeing is quantum fluctuations in the dark energy, right? Only when we get down probably 2 or 3 years maybe are we going to see the actual quantum fluctuations in the vacuum. We didn't realize that at the time, but that's one of the things that we realize now. So here are the kind of experiments that we're talking about. You see the WMAP up top corner to the Planck, the ground-based experiments, the ones at the South Pole, and the ones in the Atacama Desert. But things are getting more complicated. There are more complicated patterns in the possible correlation of CME. There are the E modes, which come from very simple sources, namely the variations in the quantum fluctuations in the infiniton field, and therefore in the matter fields that came out of that later, the matter radiation. But there also could be D modes, and you need an extra handle. You need a direction and another direction in order to make that kind of a pattern. But it turns out gravity waves can give you that, but there's another thing that can do that, and that is gravitational lensing. So we have light coming from the early universe all the way to the present, and the matter that's sort of halfway between an angular diameter distance has the most leverage to lens that, but it will also cause things to twist a little bit. And because of that, we got the theoretical description here on the left side that Douglas Scott and I do every 2 years in review, and a prediction from what we would get from the gravity waves from the universe. And there are the observations. All the observations fit the left-hand side. The right-hand side, we have no signal. This is the area in which JAXA is going to go. And here is our review from last year. We had to move the right-hand side down, the tensor side and the gravitational wave side. We had to move it down in order of magnitude from r equals 0.1 to 1, which made us have to stretch all our scales. It means the quantum fluctuations of space-time are way much smaller factor in the universe than we had thought, but it still would be very interesting to discover that. Here's a map that we can make. If you take advantage of the fact that you have this lensing, you can make a map with weighted average of the masses in the universe. And you can see it's lumpy. On a characteristic scale, it's on the order of 2 degrees. Here was the original plan for how we should improve the sensitivity of our cosmic microwave background operations. And you can see from the early times, up to Planck, up to whatever, up to CMBS4. CMBS4 is running a little late, but we can see. These are the kind of experiments that are ongoing now at the South Pole and up in the Atacama Desert. This is the JAXA mission. It's a smaller satellite, but it's still 4.5 meters across, including everything. It's a big telescope. And I end by saying the future is bright for us understanding the universe even more detail. We have the dark energy instrument up, the DAISY instrument is up. We have 3 years of data in the can. Things have been fixed, and we'll have 5 years of data in the can. We got LSST, we've got several other things. They're all on. We have LIGHTBIRD and the CBS4 coming. So the future is bright. We're going to learn a lot more about the universe. We'll have to see what the universe learns about us. So thank you.